All right, seeing that it's noon, let's go ahead and get started. Hello, welcome to Sakura's webinar series, Coastal Observing in Your Community. Thank you for sharing your virtual lunch hour with us. My name is Abby Wakely, Sakura's Communications Director, and I will be facilitating and moderating the webinar. Sakura is hosting this webinar series to discuss, highlight, and raise awareness about coastal ocean observing activities in the Southeast US. Sakura is the regional coastal ocean observing system for North Carolina, South Carolina, Georgia, and Florida. We are one of 11 that make up the NOAA-led U.S. Integrated Ocean Observing System, known as IOOS. Our mission is to sustain and promote observations that help keep you safe. This is a quick snapshot of the technology we support to accomplish our mission. I wanted to share a few upcoming Sakura opportunities, including 3 student opportunities. All proposals are due May 15th, 2020. We have the Vimbu Ocean Scholars Award, which is a $2,500 opportunity to present your research at a conference. Sakura and FACT are teaming together to sponsor a graduate student. And then our 2020 data challenge is using high frequency radar. And lastly, we are preparing a response to the anticipated U.S. Integrated Ocean Observing System 5-year proposal. We are currently soliciting letters of intent for consideration, and you can click on this link up here or go to it on your browser to learn more. All right, let's get to the reason we are all here, the webinar. All participants will be in listen-only mode. You are encouraged to type questions for the presenters or technical questions for me in the bottom right-hand chat box. I will respond to them directly or post the questions to our presenters after their presentation. We're recording this webinar today and we'll be posting the recording on the Sakura website. We're very excited to welcome Catherine Edwards from the University of Georgia Skidaway Institute of Oceanography and Travis Miles from Rutgers University. They will be presenting hurricane gliders, improving tropical storm intensity forecasts with real-time data. Catherine Edwards is a physical oceanographer and assistant professor at the Skidaway Institute of Oceanography and in the Department of Marine Sciences at University of Georgia. With programs funded by the National Science Foundation, the Gulf of Mexico Research Initiative, NOAA, and the Navy, Edwards' research focuses on answering fundamental questions in coastal oceanography and fisheries sciences with autonomous underwater vehicles, developing novel ways to optimize their use with engineering principles and real-time data streams from models and observations. Travis Miles is an assistant professor in the Department of Marine and Coastal Sciences at Rutgers University, New Brunswick. As a core faculty within the Rutgers University Center for Ocean Observing Leadership, he specializes in using networked ocean observing systems, including autonomous underwater gliders, high-frequency radar, remote sensing, and other observing platforms in conjunction with numerical ocean and atmosphere models to study air, sea, and sediment bottom interfaces. A large focus of his research includes improving hurricane intensity forecasts with processes-focused studies on highly stratified continental shelves. All right, Catherine and Travis, thank you guys so much for joining us. Catherine, I am going to promote you to presenter so you can share your screen.
Thanks so much for promoting me.
Oh, absolutely. All right, it's fast enough and I can hear you just fine.
Wonderful. So Travis and I are really glad to be here. Thank you so much for the kind introduction, Abby. Travis and I are 2 of a very large group of scientists working on the problem of improving hurricane intensity forecasts with gliders. Gustavo Goni is the lead from NOAA AOML, and there are a number of Navy, NOAA, and academic partners. I think the number is up to about 58 or so in our sort of larger network. So I want to start by acknowledging our funding, which
Catherine?
Yes.
I'm not seeing your screen.
Okay. Thank you for stopping.
Yes.
That would make it kind of awkward, wouldn't it?
Perfect. It's coming up now.
Okay, and
I see it.
Reassign Travis. Should be okay. We should be good. Okay. I want to acknowledge our funding, which comes from NOAA, from OAR, from NOAA Research, and then also through IUs. And then lastly, there are a number of volunteer and leverage partnerships that helped fund this work as well. So most of us who live in the Southeast have spent a fair amount of time on the National Hurricane Center's website during hurricane season, looking at forecast information, discussion, guidance, and graphics like these that show projections of the predictions from the hurricane's track and its intensity along the way. It can be very difficult to sometimes see a storm 3 days away from making landfall at your house and see numbers like 185 miles an hour sustained wind, and make your decisions to evacuate or shelter in place. Ultimately, these predictions are guidance for people and for emergency managers to make their decisions about evacuating, staying, and preserving life and property. Hurricanes have a clear and devastating impact on both life and property. These are images from some recent storms in the Southeast and in the Caribbean that show the devastating impact they have on human life. But it doesn't take it's not just the very strong storms that have strong impacts on life and property. Even weaker storms can cause significant flooding and also issues with storm surge and loss of power and infrastructure. It's no surprise that tropical cyclones make up a huge portion of the actual human and property costs from weather and climate disasters. Here's a summary of the billion-dollar events that affected the U.S. over the last 40 years, broken down by disaster type. And if you look at the loss in terms of money and in human life for tropical cyclones, you see it accounts for about half of the total. So in other words, tropical cyclones damages and deaths are similar to all other weather disasters combined. So we have an obvious interest in getting their forecast better so we can protect life and property. We're going to start off by giving you a roadmap of where we're going. We'll talk about the intensity problem, the problems that we run into with forecasting intensity. Then Travis will go into a case study about Hurricane Irene from 2011. And then I'll give another case study from a more recent storm from Hurricane Florence, which hit North Carolina in 2018. And then we'll discuss sort of next steps and ongoing efforts and how we see these efforts in a larger observatory of the ocean and atmosphere. So over time, it's clear we've gotten better at predicting where hurricanes are going to go. Here's a time series from the last 50 years that shows the average forecast error in terms of track error in nautical miles over the last 50 years. And you can see the slope of that curve shows that we are improving not only in our ability to forecast where the storms are going to go, but also with more accuracy further in advance, with sometimes 3, 4, and 5 days notice in advance of where the hurricane may be making landfall. To put that into perspective, here's a view of a recent cone of uncertainty from Hurricane Dorian from last year that shows the cone of uncertainty and the 5-day forecast. And if you superimpose what the 1990 cones would look like on top of that forecast, you see spatially there's a lot more uncertainty and a lot less ability to predict where the storm is going to go. If you use the numbers from 1970, it's even larger, and it's difficult to think about, how to. And so I guess the take-home lesson is that we're getting a lot better at predicting the storm's path. However, if you look at the same trends in hurricane intensity error over the last 30 years, here's a plot showing forecast error in terms of knots from 1990 to 2018. And the slope of these curves is less. We're improving in our ability to forecast tropical storm intensity, but it's not improving as rapidly. And we are able to predict hurricane intensities further out into time, but these errors still, even in the 24-hour forecast, are on the order of 10 to 15 knots, which is equivalent to about one category in the Saffir-Simpson scale. As imperfect and incomplete as the Saffir-Simpson scale is for describing the total effects of a storm, it's often it's often one of the things that people, the general public, and emergency managers use to make decisions about evacuations. You know, you can see scenarios where you might stay for a 2 but evacuate for a 3. But if there is a 15-knot error in the intensity, you may not be making the call based on the information you think is correct. More importantly, the emergency managers are using these forecasts to determine when and how to evacuate zone to protect life and property. So we want to know our zone and evacuate when we are asked to do so based on these forecasts, this guidance provided. Unfortunately, there can be a bit of evacuation fatigue if you've gone through a particularly active hurricane season, or you might remember last year that it took 8 hours to go an hour and a half down the road. And then the storm turned up being a big old nothing burger, you might be less likely to evacuate next time. So the importance of getting the forecast intensity errors down is important for people, but also for emergency managers and planners to do their jobs. So what affects hurricane intensity? What makes it so hard to predict? So, you know, with a hurricane over the ocean, the warm ocean transfers both heat and moisture into the atmosphere. You know, the heat rises, and then as the air cools, it flows outward. But then you also end up with air flowing down within the eye center. This is creating the vertical structure of the storm that we can see from satellite images. However, when under the effects of vertical wind shear, this tends to tilt over the vertical axis of the storm, which makes the process of transferring heat and humidity, heat and moisture from the ocean into the atmosphere less efficient and weakens the storm. In other ways, ocean heat feeds hurricanes, and we can use tools like satellite sea surface temperature to be able to look at areas of the ocean like the Gulf Stream that are warmer than some of the coastal ocean around it, and that may be likely to transfer more heat than other areas. But satellite SST is imperfect, and clouds can be real issues. And then it's not just the sea surface temperature that's important that can transmit energy to the atmosphere. There's subsurface heat in the ocean that matters as well. So here's an image of an ocean temperature profile that shows this is the 25°C isotherm. That represents sort of a magical number for heat and its transfer to the atmosphere to feed storms, and in a metric called the tropical cyclone heat potential. Essentially, this is an integrated 3-dimensional representation of the heat above 25 degrees centigrade that may be able to fuel the atmosphere above. This is another image from Gustavo Goni's recent paper that shows a map of tropical cyclone heat potential, showing just how warm the surface ocean, but the integrated 3D heat is in the mixed layer in areas in the Caribbean, in the Gulf Stream, and in a loop current eddy. And during Hurricane Katrina in 2005, it was shown that the storm's time over these areas of highest tropical cyclone heat potential served to fuel the hurricane more, including this final boost of intensity passing over the loop current eddy before landfall at the Mississippi-Louisiana border. But it's not just heat that matters as well. Salinity is important in regulating the transfer of energy between the atmosphere and the ocean. As a storm approaches, the winds that are associated with it can mix the surface ocean and provide that full 3D heat to the atmosphere. But salinity, freshwater layers, serve as a cap, preventing the full mixing of the full 3D heat potential into the atmosphere. So how can we as oceanographers improve intensity forecasts? What Travis and I are going to try to convince you of today is that what we can do with gliders is to represent the ocean better with three-dimensional temperature to be able to estimate THCP, to provide three-dimensional salinity measurements to be able to estimate the potential or the likelihood for mixing of some or all of that, that heat potential to the atmosphere, and also represent the ocean with processes that are too small for hurricane models to capture. And that gliders in particular are great ways to do that through real-time data that can be integrated into the forecasting process. So this is an overview of what the hurricane forecasting process looks like. There are a number of observations that are collected and aggregated from satellite, from dropsondes, from radar, from hurricane hunters and other reconnaissance. And those observations are collected, aggregated, and assimilated into ocean weather and ocean models that are coupled to create a forecast. Analysis of the data and the models are used to provide forecasts that are issued as guidance to communities and to emergency managers. And part of the hurricane gliders philosophy is that gliders can be used at pretty much each of these stages to improve hurricane forecasts by collecting subsurface temperature and salinity data, integrating those observations in real time into ocean models through data assimilation, and coupling to weather models. So that analysis from those models can integrate the knowledge gained by gliders in real time into the ocean and transmit it into the atmospheric forecasts. And Travis, I'll pass it over to you here for a discussion of Hurricane Irene.
Thank you. Let me just make sure you might have to reassign my clicking privileges. Oh, there it goes. Got it. Okay. All right. Thanks, Catherine. So Catherine provided quite a bit of background on hurricanes, observing systems, intensity, things of that nature. I'm going to walk you through one of our earliest case studies of how kind of all of this can come together. And you're going to see a few things that might be a little bit different than your traditional knowledge of this warm ocean providing heat into the atmosphere. A lot of ocean coupled processes are very regional specific, and you'll see that coming up over and over again. And the gliders have really helped us understand that particular nature of how oceans and atmospheres interact. So Hurricane Irene, I think at the time it was one of our top 10 actually costliest storms. It's now been knocked down after the last few years of really powerful storms. And it came up parallel to the US East Coast, crossed over North Carolina, right over my parents' house in Wilmington, and then went into the Mid-Atlantic Bight and made landfall in New Jersey and New York area. its track was actually really accurately forecasted days in advance, but its intensity was not. It was actually over predicted. And you can see here in this bottom left panel, this is the official forecast for Hurricane Irene. The black line is the official best track, so what the storm actually did. This is days. Each of these lines represents a forecast cycle. So there were every, I believe, 6 hours, and then maybe more frequently as it approaches landfall. And you can see over and over again, the forecast is actually going up to category 4, category 3 or 2, and even at landfall in New Jersey, it was still, some models had it forecasted as a category 2, and it was just barely a category 1, weakening into a tropical storm. At the time, we were getting significant guidance to basically leave the coastline and move inland because there was a predicted storm surge that was supposed to threaten the coastal region. This is about 30 miles inland, right at Rutgers University. And instead of storm surge at the coast, we got lots of rain inland that ended up flooding. This is a boathouse right here. And this is kind of where we do some of our operations. And here you can see the maximum rainfall. So this was a really bad rainstorm throughout the whole region, and specifically in New Jersey, kind of northeast area, we got quite a bit in this area. So as oceanographers, we started trying to figure out why we had this over prediction. Let's see, come on. Catherine, maybe, oh, there it goes. Okay, it's just a little lag. So we turn to our tools. You had that great introduction in the beginning about the Sakura ocean observing system. This is the Maracus ocean observing system. So we all kind of have our regional networks with a regional focus. This is at Rutgers University. This is in our cool room, the Coastal Ocean Observing Lab. It's a data synthesis center where we bring in all of our data products, but we also bring in people and our students. So this is a teaching and research and operations lab. We work a lot with satellite data, ranging from SST to chlorophyll. We operate 46 CODAR sites. I'm not sure if this is totally up to date, but it's between 40 and 50 sites, HF radar sites. Last summer, we passed our 500th glider deployment. And we also operate regional ocean and atmospheric models. So here's our lab, our ocean forecasts, and we use the weather research and forecasting model. And like Sakura, we're certified, so all our data can flow in real time to the IU's Data Assembly Center, and then on to the GTS, which is the Global Telecommunications System, where it can be assimilated in the model. So the glider data can go directly into our ocean models, even our coupled ocean models that are used for hurricane forecasts. So that happens in real time. So how do we use this observing system for Hurricane Irene? Well, the first thing we do is was go to our satellite products. So Irene's coming up the coast this way. This is pre-Irene. This is ahead of the storm. So we have pretty warm surface temperatures in the mid-Atlantic. This is about 28 degrees Celsius and the peak down to maybe 24 kind of in this northern area. Post-Irene, we have this massive cooling. So this cools down to about 18 degrees, 17 degrees Celsius right over the Hudson Canyon, right here in the middle. But you can see kind of throughout the whole region, there's this cold water. And if you look at the difference, our maximum cooling was actually about 11 degrees Celsius. So in hurricanes, typically 1 or 2 degrees Celsius of temperature change can have a significant impact on either weakening or strengthening of that storm. It changes the heat flux into or out of the ocean. So we started asking, did this cooling happen ahead of the storm, ahead of the eye, or was it just way behind the storm? Maybe it had no effect, it was just an after effect. Before I get into that, this cold water, the second question we had is, where did it come from? Unlike the deeper parts of the South Atlantic Bight, or kind of further south into the South Atlantic Bight, we have this cold water mass that sits at the bottom. It can be very cold, 6, 8 degrees Celsius. It persists through the entire summer into August. So this is bottom temperatures from a paper by Steve Lentz in 2017. And then this is a cross section from one of our gliders with distance from the coast and depth on the y-axis. And this is right across the shelf here. And you can see this warm water in the surface, but only down to about 10 meters depth, and then cold below. So all of our heat is in this upper layer, but right below that upper layer, right below that little crust, we have this cold water mass. And as Irene came across, it actually mixed this cold water mass up to the surface through this whole region. Now back to that timing question of when did that occur? So this is a cross section from a glider, RU-16. It was deployed right off the coast of New Jersey, right off of Tuckerton, Atlantic City, right here. And it held a position for this entire time period, about in one spot. So we look at it as a time series. And you can see time here on the x-axis, eye passage right here on August 28th at about noon. And you see this warm surface water, cold bottom water, and most of it cools ahead of that eye passage. The thermocline deepens and we get this surface cooling. So lots of cooling ahead of the storm. We start asking, why does that happen? We look at our HF radar current maps. So this is surface current maps that we get hourly. And you can actually see the eye of Hurricane Irene in the surface ocean currents right here. Oh, go back, sorry about that. You can see the eye of the storm right here in the surface currents, all this onshore flow in the surface. So you get onshore flow at the surface, you get offshore flow at the bottom. So this is a downwelling circulation, and you get this enhanced shear. And we're finding there's lots of sub-mesoscale mixing processes in these really shallow mixed layers that are causing a lot of this mixing ahead of eye. It's slightly different than what you get in the offshore environment. Okay, so we saw this in our glider data, but then we turned to our ocean models to really look at the processes. So this is a model that's run by our Marcus partner, John Wilkin. This is temperature, cross-shelf velocity, mixing, diffusion of heat. The main things here to see that in our model, we actually see that cooling and we see this vertical shear in the cross-shelf velocity. So onshore is positive here, red, and then offshore is blue. And then you get all this mixing of that temperature, vertical diffusion of heat across that interface. And we start looking at those processes to really understand this downwelling circulation. So this is just at one location for the glider, but then we looked at the model. And again, the model for the whole region captures all of that cooling across the entire continental shelf region. It's similar to the satellite SSTs as well. So we have this mixing and cooling process happening everywhere. We've looked through our gliders, our HF radar, our satellite data, and our models, our ocean models. Now we start saying, so what? What does this cooling actually do to the intensity of a storm? That is where we run our atmospheric model. So on the left, we have our, sorry, this is actually sea surface temperature, not a model. So this is just a fixed sea surface temperature that we put underneath our atmospheric model, and then a cold sea surface temperature that we put underneath another run of our atmospheric model. So we basically did a sensitivity study with different sea surface temperatures informed by our glider data, a warm case and a cold case. This warm case is what was used for the operational forecast. You don't have satellite data in advance, so you have to use what you've got. So the warm goes underneath, you get this strong storm. When you have a cold sea surface temperature, you get a weaker storm. And all of this occurred ahead of the eye. It was about a category difference between this warm case and this cold case. And when we put those winds from this atmospheric model over a storm surge model, which we used AdCirc in this case, we see differences in water level of about 1/2 meter. So with our warm case, you would have predicted about 1/2 meter more storm surge or flooding in New York City than actually occurred. So this red line is the warm case, this blue line is the cold case, and the black line is the actual measured. So we're a little bit out of phase with reality, but we have about the right height when we use these colder ocean conditions with our atmospheric model to drive that storm surge model. So in our region, we have this seasonal stratification, this cold pool that can contribute all the way into our storm surge forecast. We discovered that using our gliders, and we were able to break down each of the processes using a different part of our ocean observing system. What we're finding is that each of these particular coastal regions, so the Gulf of Mexico, the South Atlantic Bight, parts of the Caribbean, different parts of the Caribbean, all have different processes and different ocean features that hurricanes interact with and may respond to differently. So there's not just one uniform ocean that you could put underneath an atmospheric model and get it right every time. We have to start considering these individual processes. So I'm going to pass back to Catherine, and she's going to talk about some of those processes for Hurricane Florence, South Atlantic Bight, and Cape Hatteras area.
Thanks, Travis. So in the South Atlantic Bight, our sort of defining feature of the South Atlantic Bight is the Gulf Stream. It serves as our boundary condition and a real big one to deal with for all of our modeling efforts. And then really from Florida up to North Carolina, it exerts a very strong influence over not just the shelf edge, but a lot of the shelf as well. So that's where our focus is in terms of observations that can help affect hurricane intensity forecasts. With the presence and the importance of the Gulf Stream to our region, we established the Sakura Glider Observatory in 2016 to really focus on the shelf and the shelf edge and the Gulf Stream edge as part of regular surveys. We do between 3 and 5 glider deployments a year. We have a little hippie commune of glider operators in the Southeast where we do cooperative missions between Skidaway, USF, UNC, NC State, and Georgia Tech, where we pilot together, we play together, somebody deploys a glider owned by somebody else and a third person recovers it, and we all pilot together. There's a lot of shared personnel and equipment resources among our group, which lets us accomplish more together. After participating in Hurricane Gliders work in 2018, we've been able to get some funding to add 2 Hurricane Glider deployments for both the 2019 and 2020 hurricane season. So we've focused on the Gulf Stream and shelf edge really as the most important place to diagnose our models in and out of hurricane season. So Hurricane Florence made landfall in September 2018. It approached the North Carolina coast as a very scary looking Category 4 hurricane. It reached its peak on September 11th and weakened from that peak pretty substantially before making landfall about 2.5 days later. It, after making landfall, stalled, and then with about half of the storm hanging off over the ocean, stalled over North Carolina, causing significant rainfall and flooding over land, which caused a lot of the damage for it there. The intensity dropped about 50 knots between peak and landfall, and then the pressure increased about 25 millibars between its peak intensity and landfall. So in many ways, it had the same profile as Irene. We had several gliders in the water for Hurricane Florence. We deployed 2 gliders about within a week before Hurricane Florence made landfall. This is a snapshot here of Hurricane Florence's position on September 12th, as well as the hurricane forecast advisory given for that time. And the position we had of 2 gliders that were deployed. One was deployed off of Cape Hatteras on September 7th, so that's 5 days before landfall, as part of an NSF-funded effort called PEACH, Processes Driving Exchange at Cape Hatteras. And then 3 days later, we deployed a Sakura glider, Pelagia, off of Hilton Head at the North Carolina, near the South Carolina-Georgia border, on the other side of the storm's predicted path. The 3rd glider we had in the mix, we'd actually recovered about a week before the storm made landfall. The red squiggly line shows the track of Bass, the USF glider that was deployed off of Cape Canaveral, moving in and out of the Gulf Stream until it was recovered off of Wilmington on September 5th, about a week before this image was, about 6 days before peak, before the peak of the storm. And it passed right through the track where the hurricane would eventually pass to make landfall on the edge of the Gulf Stream. So let's now look at comparisons of the glider observations to ocean model predictions of temperature and salinity for those positions. So we're comparing here the glider data as a function of depth on the y-axis, and then the x-axis is temperature. Each green dot represents one measurement of temperature in each profile, and a representation of their average is shown in black here, showing very strong temperature stratification with a warm surface ocean and much cooler water in the lower layer. The blue and pink lines represent 2 Navy ocean models run at NRL. One, GOFS 3.0, includes data assimilation of surface fields, but it does not include profile data like gliders. GOFS 3.1 has a slightly different gridding system, but the importance here is that it assimilates the glider data in real time. So Maria Aristizabal at Rutgers was able to help make these visualizations comparing the glider data in real time to the model representations with and without glider data. So you can see the models that don't include glider data in assimilation show very little temperature difference between surface and bottom, but the models that do assimilate glider data much better represent temperature stratification and overall trends. You see the same pattern in salinity, which is overall less well represented, but that's not unusual. The GOFS 3.0, again, there's very little vertical structure in that model. And overall, the salinity in the model is higher than observed. But the GOFS 3.0 is able to slightly better represent the salinity stratification in this location at Cape Hatteras. And this is, again, right around the time Florence was at its peak. So the stratification by both models is underpredicted. The salinity is generally high, but the models that incorporate the glider data in real time are better able to represent the vertical stratification here at the edge of the Gulf Stream. This is a view of the spatial variability of where the glider was over its month-long deployment for the PEACH project. We deployed off of Oregon Inlet, made an offshore loop here, This is about where the glider was at on September 11th for the last plot. The glider made sort of a loop-de-loop and then ended south of Cape Hatteras at the end of its deployment at the end of the month. So we can compare a time series of the measured glider data to each of those two models over time. And again, these visualizations are courtesy of Maria Aristizabal, who's been amazing in supporting this. So this is, the upper panel shows the along track temperature in degrees Celsius. And you see this very strong stratification when the glider is north of Cape Hatteras. And there's a big difference between the warm surface water, warm and salty surface water, and the cooler and fresher water near bottom. That's better represented by the Goff's model. As the glider moves south and then beyond this front here between the MAB water and the Gulf Stream water into SAB water, there's less stratification overall, except for some time periods where you see some very fine scale structure that the Goff's 3.1 picks up in some way. But it's really nice to see this the signal of the hurricane here, and there's a suggestion perhaps of some mixing, some loss of stratification in advance of the hurricane's arrival. However, in this case, the glider was moving, so it's a little less straightforward to assign how much of that mixing was because of early bands of the storm, from interfacial processes, or from the glider moving along the edge of the front. So in general, the Gulf Stream and the Hatteras fronts here are represented better, as well as the vertical structure. But the gliders are capturing vertical and spatial scales that may not be possible to represent in these sort of larger scale ocean models. But returning back to these essential ocean features, this is a superposition of the glider's position onto, I think, the only 4 decent satellite images for the entire month of September, showing that we are right there on the edge. We are right at the edge of the Gulf Stream. We are right at the places where getting those gradients is really critical, whether you're in hurricane season or not. It's essential for the ocean forecast, and these gradients, because they exert such a heavy influence on both shoreward and away from shore, is essential for getting the ocean forecast right. And those may translate into atmospheric effects as well through tropical cyclone heat potential and measures of stratification. The other glider I'll talk about briefly now, we'll skip over Pelagia and go to Bass, the glider we deployed at the edge of the Gulf Stream off of Canaveral in August, and then recovered just after Labor Day off of Wilmington. It got to spend Hurricane Florence in the UNC Wilmington storage facility, which ended up tight and snug as a bug. It was a good place for it to be. Here's another view of those temperature comparisons between the observations from the glider and then the model representations of temperature from both Goff's 3.1 and 3.0. Again here, Goff's 3.1 does a better job of representing stratification. But I think it's worth pointing out here, we're right at the edge of the Gulf Stream in fairly large scale models where grid size is on the order of kilometers to tens of kilometers. And it's a little unfair to ask some of these models to get these gradients absolutely perfectly. But it appears that the inclusion of glider data may improve the representation of the front here and improve the representation of stratification. So these 3 gliders were 3 of about 30 Hurricane Sentinel gliders from the Navy, NOAA, NSF, and other academic and industry partners, all deployed. This is a snapshot of the gliders that were out on September 11th, 2018. So it's one measure of just how large this overall effort is. We were fortunate in a way because the storm basically came right through a number of these areas. So we were able to make a lot of these comparisons. But the idea is that these gliders can basically serve as picket lines waiting for storms to come through. You don't have to get lucky and have a hurricane drive right over your glider, or drive your glider into a hurricane. But if you go to the places that are important for capturing essential ocean features, then you're making a large improvement to the model. So this concept of operations has all gliders monitoring essential ocean features. Some of the gliders can document essential ocean processes during a storm, and maybe you get lucky and you can deploy into a hurricane like we were able to do with Pelagia. But in either case, the full glider community involvement is enabled because these observations are transmitted in real time and contributed through our regional associations to the glider DAC and available to the GTS in real time. I confess, Travis, I don't know what the analogy is to the soccer players. This is Travis's slide, but I'll let him explain that in questions.
Yeah. You know, what we're trying to build is a full soccer team, essentially. We've had hurricane hunters for, 50, 60 years, and their job is to fly, track those storms, get exactly where they are, get data in the atmosphere, drop sensors into the ocean, get the data where the storm is. The velocity for the gliders, so this is, the soccer player flying through the air going after the ball. The philosophy for the gliders is that the ocean gliders is that they're the goalies dressed in yellow. So they're protecting those specific locations all the time, as Catherine said. So with these two things combined, you start to have a full picture of where a storm is, what it's doing out at sea, but also what the ocean looks like near your important population centers, critical infrastructure, where your vulnerable populations are.
And so you can see how this infrastructure has really filled some gaps in larger observational pictures. So this is a map of the location of all Argo profiles and glider profiles from the 2018 hurricane season. The Argo profiles are by necessity taken in deeper water, and so the red marks that show where the gliders are show that they're filling really important gaps in shallower water and at the shelf edge where we're not able to get data from other autonomous platforms. This first year, we had about a third of the glider fleet that was out was dedicated for the hurricane glider task, and the other 2/3 were volunteers and other partners. In 2019, the 2019 season, I think our spatial coverage increased with a slight decrease of the number of profiles collected. But we were able to shift that balance of dedicated hurricane gliders to volunteers to be about half and half. We're in the process of getting ready for hurricane season 2020. In fact, our planning meetings and seminars are tomorrow. For those of you who are interested in the public seminar tomorrow afternoon. But this shows sort of our nominal plan for where our areas of essential ocean features are and how we plan to capture those with our glider deployments in each of our regions. We expect there to be 20 or 25 gliders, possibly more, operating in picket lines. Our version of a picket line in the South Atlantic Bight looks like a big zigzag along the edge of the Gulf Stream. We hope to do those regularly through the entire hurricane season, not just one or two, and be able to hope to try to get lucky and get some targeted deployments in as well, so we can capture the Gulf Stream essential ocean features and possibly some processes as well. We'll end up here. I'd just like to suggest that the connection between the ocean and the atmosphere goes beyond hurricanes and improving the predictions of tropical storm intensity. A lot of our weather on and near the coast and even nationally there's a big influence from the ocean. Bomb cyclones and sting jets. Meteorologists have the best names for things, don't they? But also little daily occurrences like sea breeze, why it rains every day on I-95 in the summertime, and then larger systems that have a national impact. The ocean has a role in those weather formations, and regular observations in the ocean and connection, better representation of the ocean in these coupled systems may improve the predictions of those weather systems as well. Every day there are thousands of weather balloons launched over land, and those profiles of temperature and moisture content are assimilated into the weather models to improve the forecasts over land. I think we can argue here that gliders are like the weather balloons of the ocean, and hurricane season or not, they provide critical profiles of temperature and salinity that can be assimilated in real time into the ocean models that we use at the base of our weather and tropical storm forecasting systems. So with that, I'd like to acknowledge the very large network of our collaborators. As I'd mentioned before, this is work done and drawn from an expanding network of global network of 58 institutions and growing. And so thank you so much for your time and attention.
Great. Thank you so much, Catherine and Travis. If you guys have any questions, just type them into the chat box or the Q&A box, and I will ask Travis and Catherine. And Catherine, if you want to keep your slides up just in case we need to go back to one.
Sure. Let me put my chat window too so I can see it.
So the first two questions I have, how are gliders deployed and retrieved?
Well, I can take this one. Gliders are deployed and retrieved off of, generally off of small boats, but it can be off of different vessels. The gliders move fairly slowly, about 25 centimeters a second. So we tend to deploy them closer to the locations where we want the data. Then they're able to move and go to areas of higher interest. So we deploy them off of the back of the fantail or you can deploy them off of the back of the fantail of some boat like this, do a small number of tests, and then send the glider on its way for months or weeks at a time. We're also able to do remote deployments, like the Navy does a lot of their deployments remotely with their fleet of dozens, 100+ gliders, where they have Navy vessels just dump them basically off the back, and then have their pilot and crew run and operate them from shore-based operations in Mississippi.
Great, thanks so much, Catherine. Another question is, someone is interested in the loss of tropical cyclone heat potential calculations over the continental shelf due to depth limitations. Are there any plans or a possibility of deploying gliders over the continental shelf ahead of the projected path, possibly by air, helicopter, question mark? In his opinion, these data would have been gold ahead of Hurricane Michael.
Yeah, I'll take that one. That's okay, Catherine. Can you guys hear me?
Yes.
Okay. So with tropical cyclone heat potential, that's basically the integrated temperature from 26 degrees C to the surface. In many regions, especially coastal regions, basically that metric is very small. Now, that doesn't mean that the heat flux out of the ocean and the atmosphere is very small. And so we're starting to look at other metrics in coastal zones, including mixed layer temperatures, potential energy anomalies, lots of different metrics that are a little bit more applicable to your coastal oceans. So you saw a little bit of that in Hurricane Irene. It was so cold, it was below 26 degrees Celsius the whole time. So heat potential doesn't always give you a good estimate of what a storm might do, whether it might weaken or intensify in those regions. So that's part of that. We definitely fly over continental shelves. I almost exclusively fly over continental shelves, fly gliders over continental shelves. And we think that's really important, even though it's close to shore, it's right the last 24 hours before landfall is where you might have some rapid changes in intensity. Hurricane Michael was mentioned. There was a Navy glider actually within 50 kilometers of Hurricane Michael's eye, right as it was actually rapidly intensifying. So that answers kind of another question that was further down below. It takes a lot longer to understand and interpret and write papers about the data than it does to get it to the model. So we're still looking at that and working up some research on that particular topic. The last thing about helicopters, I would love to do that. However, you can see in this picture, there's sort of these seams on the glider, these vertical black lines. They're basically separated hull sections that are sucked together with a vacuum. And so they kind of flex and bend if they undergo some sort of impact. So before you put them in the water, be gentle with them, and they're not at a state yet that you could dump them out of a plane. I think there's some engineering solutions that are being developed, smaller gliders, different classes of systems that might be able to do that in the future. So that's a great idea.
Great, thanks so much, Travis. We've had a few questions come in about the power source. How are the gliders powered and how long can they stay out at sea?
So the gliders have batteries that are installed in a couple different locations. There's a large battery about here in the forward section, some smaller batteries in the front, and then a large battery in the back. These can be alkaline batteries, just a bunch of D cells strapped together. And these gliders can typically get between 3 and 5 weeks of operation, depending on what sensors are installed with the alkaline batteries in locations like this. You can also use lithium batteries in the glider with a standard set of lithium batteries, which are fairly expensive. They're about 5 times the cost of the alkalines. You can approximately double the lifetime of the alkalines, but they do make extended sets so you can put multiple battery packs in line to get a little extra time for super long endurance missions. In most of our coastal research, particularly in the warmer water in the Gulf of Mexico and the South Atlantic Bight, you end up with enough biofouling by the 4 to 6 week mark that it's worth recovering the glider to scrub everybody off of it and look for and before redeployment. More recently, the company who builds the gliders that we use has started offering rechargeable lithium batteries, which we've begun to use in both one of the gliders in my fleet, a couple of them at USF, and then one that I operate owned by Sakura. Those let us not only, instead of having to wait for reballast the glider, get the weight perfect, and redeploy, we're able to basically recover the glider, plug it in to recharge the batteries without even having to open the glider and be able to redeploy. That lets us redeploy quickly from larger ships where we're able to be offshore for at least the 12 to 16 hour charge time, but also reduces the risk of leaks from having to open and close the glider to fool with it when you have a quick redeployment cycle. So with those, we're getting between 3 and 5 weeks, depending on the sensor package.
Great, thanks so much, Catherine. And seeing that it's 12:59, I'm going to ask one more question. And if we did not get to your guys' questions today, I'm going to pull them all together and have Catherine and Travis look at them, and we will answer them for you guys and get the answers emailed to everybody. So the last question I have, what is the optimal number of gliders for improving hurricane forecasting? Is the current number sufficient, and where are the major gaps?
Well, I think if you ask either of us, we would say there's never enough, right?
Yeah.
This is our job. We want as many as possible. I think I think those answers are dependent on the scale of the features that we need to represent. Because the gliders move fairly slowly, you're not able to capture a synoptic survey along an edge, along a feature. So, you know, if you were doing a science study of capturing the Gulf Stream edge properly, you'd have like an army of gliders out there. And the Navy has taken a lot of that approach. I would love to see many, 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 many more. But I think a better analysis of scales and which scales are most important for the models to resolve is probably worthwhile. Travis, any additional thoughts?
Yeah, I think you know, as oceanographers and scientists, we could easily say unlimited, but we do write budgets too, so we understand limitations. Um, I think our approach on this topic is that we haven't had enough yet to actually determine if we have enough. So basically, we need to do what are called observing system simulation experiments with models to simulate a simulation of glider data into those models and see what those actual built out networks need to be. So we can actually do this work with models with no data in the water, and then we can come up with a strategy and go and test it. We have had some limited work on that in the Caribbean. So they're building out a plan for the Caribbean. But the regions, some of these other regions, we have some hypotheses of, you know, in the mid-Atlantic, maybe 5 gliders, we think, based on the scale of the features, but those really need to be tested, and there are methods for testing those if we have the funding and tools and the support to do that. So we're trying right now to get as much data as we can and archive it. That way we can do some of those experiments in the future. So.
Great. Thanks so much, Travis and Catherine. And we still have questions coming in, so we'll make sure that we can get them all answered. And somebody asked, will we be able to post a PDF of your presentation on the Sakura website?
Sure, we can make a version available.
Okay, perfect. Great. So I will send everybody a recording of the webinar along with a PDF of the presentation. It usually takes about a week to turn it around. Thank you guys so much for presenting. And once again, if we didn't get to your questions, we'll try our best to answer them over email. Thank you, guys. I am going to take back over and end the webinar. Everyone have a great Tuesday.
Thanks, everyone.